All right, so the next step in our process for finding the energy changes of reactions that we maybe can't conduct directly in the laboratory is to branch out to a larger group of reactions that we can use as those little puzzle pieces that we just added together, like our generic A, B, D, E case that we just had. And in chemistry, we're going to use what we call the formation reaction. Because every chemical compound, we could imagine it being made directly from its elements. And if we wrote that reaction down, that's what we term a formation reaction. Now, it's not necessarily how that chemical would get made in the context of a laboratory setting that we might be working in, but because that reaction exists, we could use it in our Hess's law procedure, as I'll show you. But let me tell you a little bit about these formation reactions first. Again, formation reactions, what they are, or their purpose, is to show a compound being made directly from its elemental components, all right, from the elements directly, not from some other compounds breaking apart, for example. And then all reactions have some energy change, so do these formation reactions. Specifically, the energy change of a formation reaction, we refer to it as the enthalpy of formation. Give it a little bit different insignia than we've been using. Delta H, that's the same, but we change the subscript to F. And this superscript of a 0 corresponds to the word standard. So we've standardized this across chemistry so that everyone reports their values at the same conditions of temperature and pressure. 25 degrees Celsius and 1 atmosphere are the thermodynamic standard values for temperature and pressure. All right? So when you propose a reaction occurring in this fashion, elements forming a compound at 25 degrees Celsius and 1 atmosphere, the energy change in that setting is called the standard enthalpy of formation. So let's look at a couple of compounds. Carbon dioxide. How would we make carbon dioxide? Well, the universe provides us with solid carbon as an element and O2 gas as elements, and look at that, they would add together to make CO2 in the gas phase, which is what it would normally exist at 25 degrees Celsius. The enthalpy of formation of this reaction is negative 393.5 kilojoules per mole of carbon dioxide that we make. And so anytime carbon dioxide now shows up in a reaction, it doesn't necessarily have to be made this way directly, but now anytime CO2 is in a reaction, we can use this as one of those puzzle pieces, one of those reactions that we're having as part of the addition process that we did in the last video segment. All right. Sodium chloride. How would we make sodium chloride from its elements? Sodium is a solid metal, and chlorine is Cl2. That's its formula. It's one of the 6 or so diatomic gases that exist, along with hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. Those are all our diatomics that we have. But this isn't balanced. This does not equal 1 mole of sodium chloride. And a formation reaction is always going to show 1 mole of the product. So we have to do something that's a little bit unusual. We're not used to writing them, but we can write fractional coefficients in our formation reactions. All right? And that fraction, it's going to be pretty easy to find. It's going to be the number that you want over here in your final formula divided by the subscript of that element, usually going to be a 2, right, for those diatomic elements that I just mentioned over here. All right. So sodium chloride has an enthalpy of formation of negative 411.1 kilojoules per mole. Okay. Ethanol, one more, a little bit more complex molecule here. Got 3 elements to consider, and we'll need some different coefficients. So if we wanted to make ethanol from its elements, we would need 2 units of carbon, 2 moles of carbon, Okay? We would need 6 total atoms of hydrogen. Hydrogen is another of our diatomic elements, H2. So the 6 that we need, total of 6, divided by the 2's, units in which it comes, means we need 3 entire molecules of hydrogen. And then we need some oxygen, but oxygen again comes in O2, so we only need half a mole of oxygen. And this would be our C2H5OH in the liquid phase. And so its enthalpy of formation is negative 277.0 kilojoules per mole. Now the phase is particularly important because ethanol could also be formed in the gas phase. The reaction would look exactly the same, except that you would form the ethanol in the gas phase. In the liquid phase, as I've just given it to you, the enthalpy of formation is negative 277. But in the gas phase, the enthalpy of formation is negative 234.8 kilojoules per mole. So depending on how your ethanol might show up in a chemical reaction, that's a pretty significant difference of 40 or so kilojoules per mole of ethanol. So when you're using these formation reactions, you need to pay careful attention to what phase the material is in. Water also falls into this category just like the ethanol does. All right? It shows up in liquid in some reactions and gas. So we want to make sure that we're very carefully examining the phase that something is listed in. All right? Quick notes here. Notice that these are all negative values. That's not true of every single enthalpy of formation, but most materials do have a negative enthalpy of formation because you're taking these elements and by bonding them together, you're lowering the total energy that they have. So that's the energy that's then released, which corresponds to a negative sign for the energy change in a reaction. So you will see a lot of negative enthalpies of formation. I got all of these values out of Appendix 2B in your textbook. That's going to be a very important resource for you for the remainder of this chapter. And you want to make sure that you're using the Appendix 2B values, that you're not just web searching for delta H formation values when you're doing your mastering chemistry homework, because recall that, maybe you learned this lesson in Chem 1, the answers in Mastering Chemistry are linked to constants in your textbook, as they're listed in your textbook. And there might be minor variations in these values depending on the sources. So you could be doing the problem correctly, but if you used a slightly different value for one of these delta H formations, you're not going to get the correct answer as far as mastering is concerned. Right? So I'll take a quick pause here, and when I come back, we'll put these formation reactions into action using them in Hess's law to find the enthalpy change of a larger reaction.